Thanks. Good morning, everyone, and welcome to this talk, where we're going to look out for a crystal ball that will help us to not only identify, but also prioritize technical debt. So let's jump right in and see what this is all about. My starting point is Martin Fowler's well-known definition of technical debt. And what I want us to do here is to focus on the key aspect. And the key aspect of technical debt is that just like its financial counterpart, technical debt incurs an interest payment. And this is something that I've found that we in the industry, we tend to misuse and sometimes misunderstand. And the consequence of that is that technical debt, the concept, is not as useful or helpful as it could be. So let me show you what I mean about that by having you do a small experiment. So what's going to happen now is that I'm going to put up a piece of code here. And your task is to judge the quality of that piece of code. All right? Ready? You do look ready. So have a look at this beauty. How many of you think that this is excellent code? How many would let this through a code review? So, looks like we are just two of us. Of course, this is not good code. This is not the kind of code we write. And of course, we would never write something like that ourselves. Never, ever. Right? But is it a problem? Is it technical debt? Without more context, we just cannot tell. Because it's not technical debt unless we have to pay an interest rate on it. An interest rate, interestingly enough, is a function of time. So in order to identify technical debt, we will need to have a time dimension into our code. Where can we get such a thing? In a few minutes, I'm going to show you one technique. But before we go there, I would like to share a little story with you. As part of my day job, I go to different companies and I analyze their code bases. And a while ago, I worked with a company that prior to my arrival, they had used a tool capable of quantifying technical debt. So they had taken this tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years. Just to put it into perspective for you, 4,000 years ago, that was here, when Moses parted the Red Sea. So, 4,000 years of technical debt may well be accurate, but it's not particularly helpful. I mean, where do we start? Is all debt equal? Besides, I actually think it's a mistake to try to quantify technical debt from code alone. And the reason I say that is because most technical debt isn't even technical. And this is something I find over and over again, that we as developers, we tend to mistake organizational problems for technical issues. And the consequence is that we start to address the symptoms instead of the root cause. So just to give you some quick examples, perhaps you have seen this, that you come into a new company, right? And someone helps you the first day and tells you, all right, but be a bit careful with this part of the code. It's a complete mess. It's really, really hard to understand. Or my personal favorite, you might have heard this one. We spend a lot of time merging different feature branches. We need to buy better merge tools. Have you heard that one? Some of you nod, yeah. So as you will see, there may be an organizational side to that. And we're going to discuss that later. But I think that the main reason that we make misattributions like this is because the organization that builds the code is invisible in the code itself. And that's unfortunate because there is a strong link between technical debt and the organization. And I'm pretty sure that we cannot address technical debt without taking a holistic view of it. And that holistic view has to include a social dimension. So based upon what I have told you so far, I put together kind of a wish list, kind of the information I think that we need in order to address technical debt. And the first thing, our starting point, is to find out which part of the code has the highest interest rate. The second aspect is, does our architecture support the way our system evolves? Are we working with or against our architecture? And the third and final and perhaps most important point, how does it look from a social perspective? Are there any productivity bottlenecks? You know, those pieces of the code where 5 different teams have to work together all the time. Now, please, think back to the project you work on right now. Do you think this kind of information would be useful to you in your day job? I see that some of you are nodding. That's very good. You're going to enjoy the rest of the session. What I want you to focus on here is that none of this information is available in the code itself. Most importantly, we lack some critical information. We lack a time dimension, and we miss social organizational information. So how can we get that? Where's our crystal ball? It turns out you all already have one. We're just not used to think about it that way. I'm talking about our version control data. So this is a simple example from Git. And version control is amazing in that it's actually a behavioral log. It tells us exactly what parts of the code we have changed at what point in time. So we get the time dimension, right? And based on that time dimension, we can calculate a lot of interesting statistics and frequencies. But even more important, version control data is social data. So we know exactly which programmer that worked in which parts of the code. So let's embrace version control data, and let's see how it helps us find code with high interest rate. And my starting point here is a concept I call hotspots. Let me show you how that works. This is a hotspot analysis of a well-known Java system, Tomcat. Has anyone worked or used Tomcat? Yeah, a lot of you. Cool. So Tomcat is a mature system with a rich history, and I'm going to show you how to interpret this visualization. So have a look at those large blue circles that blink right now. Each one of those represents a folder in the Tomcat repository. And you see that you have other smaller circles inside it. Those are subfolders, right? So this is a hierarchical visualization that follows the folder structure of your code. It's also interactive, which I think is important once we get to systems of scale. So you can zoom in on the level of detail you're interested in. And if you do that, you will see that each file is represented as a circle. And you will see that the circles, they have different size. That's because the size is used to represent the complexity of the corresponding code. Now, how do we measure code complexity? Yeah, we have a bunch of different ways, right? I guess most of you are familiar with things like McCabe's cyclomatic complexity. We also have things like Halstead's volume metrics that we could use. And it doesn't really matter what kind of metric you use, because what they all have in common is that they're equally bad. Complexity metrics are terrible at measuring complexity. So what I tend to use is the simplest thing that could possibly work, which in this case is the number of lines of code. It has a very high correlation to things like cyclomatic complexity. And besides, this is not the interesting part of the data. The interesting part of the data is, what's the interest rate? So what we're going to do is that we're going to pull out some data from a version control system and look at the change frequency of that code. So how often do we actually need to work in that part of the code? And when we combine those two dimensions, we're able to identify complicated code that we have to work with often, and that's our hotspots. So let's return to Tomcat. And you see that in Tomcat, the hotspots, there are relatively few hotspots, right? Now, just because something is a hotspot, that doesn't mean it's a problem. What it means is that this is the most important part of the code when it comes to technical debt. So you want to inspect that code and ensure that the code is nice, it's clean, it's easy to understand, it's easy to evolve, because that's where you spend most of your time. However, in practice, more often than not, I found that the opposite is true. And that tends to make hotspots great refactoring candidates. And there's a fascinating reason why that's the case. And I want to show you why by borrowing a quote from the great George Orwell. Perhaps you remember, those of you who have read George Orwell, that he actually said that all code is equal, but some code is more equal than others. Now, what do we mean with that statement? Well, let me show you. Please have a look at the following graphs. They all show exactly the same thing. So on the x-axis, you have each file in the system, and they're sorted according to their change frequency. That is, how many commits do I do to each file? And the number of commits is what you see here on the y-axis. Now, if you look at the 3 examples here, you see that those represent 3 radically different code bases. They're implemented in different languages. They target different domains. They use completely different technologies. They are developed by different organizations. They have a different lifetime span. Everything is different. Yet, do you see any patterns? That's right. They all show exactly the same distribution. They show a power law distribution. And this is something I've found in every single code base that I've analyzed. This seems to be the way that software evolves. And this is important because this gives us a tool to prioritize. Because what this means is that in your typical code base, most of your code is here in the long tail. It represents code that you rarely, if ever, need to work with. And most of your development activity is focused to a relatively small part of your code. And that's where we want to focus improvements in order to be pretty sure that we get a real return on that investment. So hotspots are a great starting point, but sometimes they are not enough. And I want to show you an example where hotspots doesn't quite work. And I want to show you a different case study. This is a hotspot analysis of the .NET Core runtime from Microsoft. And when I did this analysis, it was like 6 months ago, most of the hotspots were here in the JIT package, the just-in-time compilation support, right? But you also see there's kind of like a satellite hotspot here, something called gc.cpp. That's the .NET garbage collector. Now, gc.cpp looks quite innocent here on screen, but that's just because the scale of .NET Core. .NET is huge. It consists of, what you see here on screen is approximately 4 million lines of code. And gc.cpp is a relatively big file. How big? I have no idea, so let's look it up on GitHub. Wow. So pretty big, right? So we need to look at the raw file, and when we do that, we will see that gc.cpp is a file with 37,000 lines of C++. 37,000 lines of C++. Let me tell you, I used to be a C++ developer. I did C++ for 10 years. And yeah, I know what you think. That's 10 years I never get back, right? And I kind of agree, but at the same time, it gives me a lot of respect for 37,000 lines of C++. It's the stuff nightmares are made of. And besides, how useful is it to know that gc.cpp is a hotspot? So let's pretend I come to your organization and say, hey, look, I found your worst maintenance problems. I found your technical debt with the highest interest rate. You just rewrite this file and everything is fine. Again, it would be accurate, but not particularly helpful, right? So we need to do better. Because how do we act upon such information? The answer is we don't. So what I suggest is this. When we identify those big hotspots, what we do now is that we take the source code and we parse it into chunks of different methods. And then we look at where does each commit hit, right? So it's exactly the same measure, but on a function method level. Let me show you how that looks on gc.cpp. So a hotspot analysis on a function level reveals that the number one hotspot on a function level is a function called grow brick card tables. That function consists of 332 lines of code. That's kind of a lot for a single function, isn't it? But it's definitely much less than 37,000 lines of code, which is the size of the total file. And it's definitely less than 4 million lines of code, which is the size of a total system. So even more important, we are now at a level where we can act upon the information and do a focused refactoring based on how we have worked with the code so far. So we're going to return to the hotspots, But before we do that, I would like to kind of try to answer a question. Like, how do you get to a file with 37,000 lines of C++? I really can't let that go. So this is a book recommendation from me. This is the best book I know on how organizations fail. It's written by Diane Vaughan, and Diane Vaughan, the interesting thing here is she's not a software developer. She's a sociologist, and she used the Challenger accident to coin her theory of normalization of deviance. So how many of you remember the Space Shuttle Challenger? Yeah, so like half of you maybe, right? So let's do a quick recap on what happened. So this is the Challenger on its final launch. And that's the actual space shuttle. And what you see here is this huge object. That's a solid rocket booster. That's a huge thing, right? It's so big, so it's delivered in 3 separate segments that are then assembled. And what you see here is a puff of gray smoke. You see it? Not a good thing. It's not supposed to be there. So what actually happened was that here's a joint between 2 different segments, and that joint failed to seal, and the consequence was that some hot rocket gases could escape and impact the whole structure of the Challenger. So the spaceship basically disintegrated once it got into the air. And when Diane Vaughan writes about this, she tells the story of how already back in the 70s, when they made the first design tests on the Challenger and the solid rocket boosters, it turned out that the actual performance of those solid rocket booster joints deviated from the predicted performance. What do you do in that case? Well, this is NASA, so they formed a committee. And they discussed the problem, and they decided to pass it off as an acceptable risk. Years later, during the first in-flight tests, again, it was revealed that the actual performance deviated from the predicted performance. Again, they discussed the problem and passed it off as an acceptable risk. And it went on and on like that for years, before actually on the very eve of the launch, there were some very real concerns raised by some of the engineers working on this stuff due to the unusually cold temperatures in Florida at that time. Again, it was discussed and passed off as an acceptable risk. And the consequence was a tragic loss of lives. Now, this is what Diane Vaughan calls the normalization of deviance. That each time we accept a risk, the deviations become the new normal. We get a new point of reference. And this is interesting because this is not really about spaceships. This is about people. And we have plenty of normalization of deviance in software too. So let me give you an example. Let's say that you join a new organization and you inherit a file with 6,000 lines of code. Wow, that's a lot. But if you work with that long enough, that becomes your new normal. You start to get to know those lines of code. And I mean, besides, seriously, what difference would it make with a few extra 100 lines of code, right? So soon we have 7,000 lines of code. Then we have 8,000, and so on. So we need to find a way to identify and stop the normalization of deviance. Here's one technique that I found really useful for software. This is something I call complexity trends. And the way this works is basically that when I find a hotspot, I pull out all historic revisions from the version control data of that code, and then I measure the code complexity at each point in time and plot a trend like this. So all systems, they tell stories, right? We just need to learn to read them. So here's an example. So you see the blue line shows the growth in lines of code. The red line is one of the complexity metrics, like cyclomatic complexity. And you see here that there was some kind of refactoring done here back in April, right? But somehow they seem to have failed to address the root cause because pretty soon the complexity starts to sneak in back again before there was a dramatic increase here just at the beginning of the year. So this is a warning sign that we need to take a step back and consider what actually happens and in the direction that this code grows. So the normalization of deviance is one of the reasons why whistleblowers are so important in organizations. And I have found that complexity trends make great whistleblowers in code. So to sum up this first part, hotspots help us identify that code with the highest interest rate. And the reason they work is because all code isn't equal. What I want us to do now is to climb up the abstraction ladder and look at the architectural level and try to find out how well does our architecture supports the way our system evolves. And as you all know, you cannot really talk about architecture without mentioning art. So does anyone recognize this piece of work? None of you. That's a good thing, because it doesn't exist. This is something called a liquid crystal light projection, done by the artist Gustav Metzger. So this is an object that changes all the time, right? So this work of art looks completely different today than it did yesterday. It's kind of fascinating to watch it. Now, the interesting thing is the way it changes, because the way it changes is that any new form necessitates the destruction of an existing form. And this is exactly how code is supposed to evolve. So successful code will evolve, and it will change, and that's a good thing. However, the reason I say it's auto-destructive is because changes and new features, they often become increasingly more difficult to implement over time. And some systems, they just seem to reach some kind of tipping point. And beyond that point, they get virtually impossible to maintain. So how can we catch that? How can we detect that? Well, we have our hotspots, right? But I would say that the file level makes it pretty hard to reason about the macro aspects of the system. So we would like to raise the abstraction ladder a little bit. So one way of doing that is this. Instead of measuring hotspots on our file and function level, let's introduce logical components by taking a set of files and aggregating all contributions to that file and put a logical name on it. So we can have our logical components follow the folder structure of your code if you want. That's quite typical. You can use any kind of mapping here that you want. The only important thing is that whatever group or maps you introduce for logical components, those should carry an architectural significance in your context. So once we do that, we can start to reason about how our system evolves. So let me show you a specific example from a service-oriented architecture. So what I would do in this case is that I would introduce a logical component for each service here. And then I would measure hotspots on that level of services. Now, when we do that, we get help to answer one of the most important questions we have about microservices. And this is a serious question, right? I mean, serious in the way that flame wars have been fought about it, friendships have been ended. And the question is, how big is a microservice supposed to be? 100 lines of code, 1,000, 2,000. We know it's a bit misdirected to reason about service size in terms of lines of code. Because what we're actually after is business capabilities. We want each service to implement a single business capability, right? So the key here is cohesion. So once we start to measure hotspots on this level, we can identify hotspot services. So this is actually some real data from a real system, and we see that the number one hotspot here is something called the recommendations service. We see we have done a lot of changes to that piece of the code, and it now consists of around 5,000 lines of code. Now, just that we calculated complexity trends for individual files, we can aggregate the contributions from multiple files and get a complexity trend of a whole service. And we see that this service is pretty much, was some rapid initial development, and now it seems to have stabilized on that higher level of like 5,000 lines of code with a lot of changes all the time, but without any significant growth. And this kind of data, it doesn't really solve any problems. What it does is that it helps you ask the right questions. And the question here is, if that service with 5,000 lines of code that changes all the time really represents a single business capability. Perhaps it's a service that's better off when split into 2 parts or 3. But we can do even more with this kind of data. And I would like to show you how by introducing a concept called temporal coupling or change coupling. Here's how it works. Let's say we have 3 different subsystems. The first time we do a change to this system, we modify the fuel injector and diagnostics module together. The next time we do a change, we modify something else. The third time, we're back to modifying the fuel injector and diagnostics module. Now, if this is a trend that continues, there has to be some kind of relationship between those two subsystems, right? Because they keep changing together. This is something we can use to reason about the architectures. And I want to show you an example from a few different architectural styles. And I would like to start by talking about layers. Why layers? Well, because layered architecture have been so popular, so a lot of what we call legacy systems are implemented in layered styles. So this is basically the canonical building blocks of a model view controller. And as I analyze code bases for a living, when I come to a company, I always ask them, what kind of architectural style do you have? And they often tell me that, yeah, we're using a model view controller or a model view presenter or model view model or some of those variations, right? And then you look at the code, and that's never what the code looks like. And the reason for that is that we all know that this is not enough, right? We need a services layer too, right? Of course we need a services layer. And below that, we must have a repository layer. And the reason that we must have a repository layer is because I actually have no idea. So let's call it a best practice, shall we? And then we need an object relational mapper below that, because we don't want to access the SQL directly. And then maybe we have some SQL. And we all know that in reality, it's quite likely that we have a few extra layers, right? We may have a view helper or something like that. Now, this is interesting, because if we do a temporal coupling measurement on this level, where we consider each layer a logical component, what does our change pattern actually look like? Here's what they look like. I have found, and this is real data from real systems, that somewhere between 30 to 70% of all commits ripple through the entire architectural hierarchy. And this is kind of interesting, because it impacts what we can do with that system. So what this means is that few changes are local, right? And I have found that work like this, the architecture like this, is basically built around a technical partitioning into technical building blocks. But the kind of work we do is feature-oriented, it's end-user-oriented. So there is a kind of conflict between those two styles and the kind of work we do. Now, I've found that layered architectures may work really, really well for small teams. Where I have seen it work less well is when the team is a little bit larger. And I think the cutoff point is as low as 4, maybe 5 people. So if you have a larger organization, this may very well become a real problem. And it may become a real problem because now you have all developers working all parts of the code all the time. Not only is that quite an increased coordination overhead, it also puts you at risk for things like unexpected feature interactions. And I would like to claim that one of the original motivations for layered architectures is this, a separation of concerns. But I will claim that if most of our commits have to ripple through all the layers, perhaps, just perhaps, it's the wrong concerns we are separating on. And I think this is one of the main reasons also due to the recent popularity of things like microservices. And you all recognize this, right? Because that's what microservices look like in PowerPoint. In reality, we know that microservices, they are much, much more complex, right? So we have shared building blocks, we have service templates, we have client APIs, we may have cross-cutting concerns like diagnostics and monitoring and all that stuff. So that additional complexity, it comes with a risk. And that risk is coupling, which is like the cardinal sin in microservices, right? Tight coupling. So that's something we want to avoid. Because the moment we start to couple different services to each other, we lose a lot of the advantages of microservices, and we are left with an excess mess of complexity. So if we have an important architectural principle like that, why don't we measure it? So again, let's consider each microservice a logical component, and let's measure temporal coupling on that level, so that we can detect patterns like this. Change patterns that ripple across multiple repositories. And if we start to use that from the very beginning, we can use that as an early warning system and prevent those things from happening. And if we do that, we can avoid things like what I call the microservices shotgun surgery pattern. Now, what's the microservices shotgun surgery pattern? That's basically the idea that you want to tweak a single business capability, and you end up modifying 5 different services. And there are several reasons why that may happen. The reasons I've seen that are most common is, first of all, that those different services, they may share code that itself isn't stable from an evolutionary perspective. Another reason I've seen that some services are just leaky abstractions, and other services tend to depend upon their implementation details, which makes them change together. I've also seen that this tends to be a bit more common when the same team is responsible for several services. It seems to become much, much easier to send more directed information and assume more about the receiver. So, what tools do I use to analyze these kind of architectures and to do a hotspot analysis and temporal coupling analysis? Well, when I wrote my book, like 3 or 4 years ago with Your Code is Cramps in, there weren't really any tools available that could do the analysis I wanted to do. So I put together my own tool suite. It's available on my GitHub account. It's open source. Just download it, play around with it. It's a pretty good starting point if we want to start to get a feel for what this kind of analysis can do to you and can do for you. So what I'm working on right now is something called CodeScene that you can have a look at CodeScene.io. I have a bunch of different case studies there. It's free to use for open source projects, so if you work in that space, have a look at it. There are also some interesting options from the academic space. My personal favorite is this one, called the Evolution Radar, which is particularly strong on change coupling. It's a really, really good tool for that. And finally, if you want to create your own tools, I recommend that you have a look at the Moose platform. So the Moose platform is a platform for building code analyzers. Moose is also the best excuse I know to learn to program in Smalltalk. It's a wonderful language. So, to sum up this part, we have seen that our hotspots, they scale to all different levels. We can use the same measure on a function level, on a file level, as we can on an architectural level. And we have seen how we can use temporal coupling to evaluate our architectures, the evolution of them. Now, I want to spend the final minutes of this presentation on exploring the social side of our code. So let me start by asking you, how many of you develop software as part of a team? So that's like 99.9% or something. So most of you, right? And that's what we have to do, because we take on larger and larger problems. Our systems become more and more complex, and we simply cannot work on them alone. So we need to get together in a team to achieve what we want to achieve. However, what I want you to know is that teamwork is never free. Teamwork always comes with a cost. And that cost is what social psychologists call process loss. So process loss is a concept that the social psychologists, they've taken it from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. So let me show you how this model works. So we have a bunch of individuals, and together they have a potential productivity. That's never what we get out of a team. The real productivity is always somewhat smaller, and part of the potential is simply lost. How is it lost? Well, the kind of process loss you get depends upon the task you do. But I would say within something like software, most of the process loss is coordination and communication overhead. And you may also have software aspects, like, for example, motivation losses, which is a very real thing in several projects. The bad news are that you can never avoid process loss entirely. You can never eliminate it. But what you can do is to minimize it, of course. So let's look at another common source for process loss. This is another concept from social psychology called the diffusion of responsibility. And the diffusion of responsibility is something that you can experience if you're unfortunate enough to witness an emergency or an accident. Because it turns out, the more bystanders, the more people present when something happens like that, the less likely that any individual will offer help. It's kind of scary, isn't it? And there are several reasons for that. One common reason is, of course, that the more people present, we just assume that, oh, well, someone else will help instead. And we have plenty of diffusion of responsibility in software too. And now I'm going to talk a little bit about a very, very, very controversial topic. The kind of topic you never talk about on a conference, right? It's stupid to do that, so I'm going to do that. I'm going to talk about, believe it or not, I'm really scared to say this, but I'm going to talk about code ownership. Wow. So, and I want to talk about it because I want to make it clear that when I say code ownership, I don't mean ownership in the sense of, hey, this is my code, stay away. No, not at all. I mean code ownership in the sense that someone takes a personal responsibility for a piece of code, and for its quality and for its future. And that someone could be an individual, it could be a pair, or it could be a small team within a large organization. So things like that help us minimize the diffusion of responsibility. And if we have an important principle like that, we should try to supervise and measure it. Here's one way of doing that. Since we're in version control wonderland, we have access to all that social data. So we know exactly which individual that worked on which parts of the code. What we can do now is to aggregate individuals into teams, right? Because that's the interesting level to operate and measure on. So let's see how a diffusion of responsibility metric looks like. So it's the same kind of visualization that we saw earlier with the hotspots, only now the color carries a different meaning. The color shows the amount of inter-team coordination. So the more often different teams work in the same parts of the code and the more fragmented their development efforts, the more red the corresponding module and file here. Now, how do we use this data? Well, we have an area here with a lot of potential, a lot of excess parallel development by lots of different teams. How do we react to that? Well, it's really, really hard. There are in general two things that I've seen work. The first thing is that you start to investigate that part of the code from a technical perspective. Because you will find that code changes for a reason. And the reason that part of the code attracts so many different teams is probably because it has many reasons to do so. It has too many responsibilities. So you will see that if you take that code and you identify those responsibilities and you split it according to responsibilities, not only will you get a more cohesive system, you will also get a system that helps you minimize the amount of coordination needs between different teams. Another thing that you may find from time to time is that your organization may lack a team to take on a shared responsibility. So you may actually have to introduce a new team to take on that ownership. But we can do so much more with version control data. We can start to measure things like Conway's law, right? So here's an example. Now, this time, the contributions of each team are marked up with different colors, right? So each team has a unique color. And here we can see this is a package by feature architecture. And you can see basically each circle here represents one feature. And you see from the perspective of Conway's law, this looks absolutely wonderful, doesn't it? Each team works in perfect isolation with a minimum of coordination overhead between them. Is that the way we want to go? I'm not sure, because I don't know. I have to make a confession here. All data that you have seen so far are from real-world systems, except this one. I had to fake it, because I've never seen that happen in reality. And I don't think it's a good idea to go all that way. I'm not going to talk so much about that, but I think when we separate teams too much, we run the risk of falling into a lot of different social traps that may be more expensive than the actual coordination itself. But please ask me about that afterwards, and I'll be happy to talk about it. But now, I want to show you a more realistic example. The next one is real data. So this is an organization I worked with a couple of years ago. And what this organization did was that they decided to introduce feature teams. So they took their existing organization and sliced it into 12 different teams. And then they worked in sprints. So at the beginning of each sprint, each team got assigned a number of tasks. And then they get working on the code base. And this is what the contribution patterns look like after 1 month. Do you see any patterns? Neither do I. This is basically collective chaos. And the reason I say that is because what happens here, this is a coordination nightmare, because what happens here is that you have basically 12 different teams working in the same parts of the code all the time for different reasons. So not only is there, and you need to start to put processes and stuff on top of that in order to be able to control the quality at all, and it's going to be really, really expensive. Another thing that's going to be expensive is that in this case, you miss synergies between different features. So that is, you miss opportunities to simplify not only the problem domain, but also the solution domain. So please, align your architecture and your organization. Your code is going to thank you for it. Now, I hope you have enjoyed this journey through the fascinating field of evolving code. And ultimately, it's all about writing better software. Software that can evolve with the pressure of new features, novel usages, and changed circumstances. And I'm pretty sure that writing code of that quality is never going to be easy. So we need all the support we can get. And I hope that this session has inspired you to investigate the field in more depth. If you want to read more about this, I have 2 books about the topic, Your Code is a Crime Scene, and my new book, available from a pragmatic bookshelf now, Software Design X-Rays. I also blog a lot about this. So if you look at Empear.com, our blog, I have a lot of different case studies from different open source systems there that you can read about. And now, before I take some questions, I'd like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thanks. Thanks.
Yeah, thanks a lot for the talk. So there are some questions that came in through the app. One of them is, I think, quite an interesting one and a common one. What's the best way to sell the necessity of code refactoring to stakeholders and management?
Sorry, one more time.
What's the best way to sell the necessity of code refactoring to stakeholders and management?
Oh, yeah, that's a good one. Yeah, so it's actually not that hard. So what I think we need to do is that we need to bridge that gap between us developers and management. And the way to do it is by ensuring that we kind of speak the same language. We have to I think it's mostly our responsibility as developers to give management a glimpse into our world. And several managers are non-technical, they don't code, perhaps they've never done it. And so what I've found is that visualizing the stuff really, really helps. The hotspots tend to be quite intuitive. Most managers tend to understand them, that yes, this is really where we work all the time. So they tend to, because what they are afraid of is, of course, to make a decision like, all right, let's go ahead. Here we have a refactoring budget, start to improve this stuff, and then you don't get any effect out of that. So if you show them real data, they can base their decisions on data, which makes them feel much more comfortable. I've also found that visualizing things like complexity trends helps a lot. Because what I find in practice is that when I identify a hotspot in a large organization, and I look at the code and I see, yeah, this is really, really tricky, we really need to do something here. Then you look back in time and you see that this code has probably been a problem for years. And trends are really, really good at visualizing that. So you can see that, all right, you work most of your time in this part of the code, and as you do, it becomes more and more and more complicated. All managers understand that that's not a good thing. So that's my recommendation. Put numbers on it instead of just relying on a gut feeling, and visualize it.
Another one is, can you have examples of process gains opposite of process loss? For example, when a developer works together with a domain expert on a domain-specific development project.
Yes, of course you can. And we do have a lot of process gain too in that way, but I'm really sorry to say, but that's not something I can measure, unfortunately. But yeah, it's definitely a case.
Okay. So you recommend for limited cross-team coordination. what would such a process look like?
So I think there's an important distinction to make here, because what we want to do is basically we want to minimize the coordination need between different teams. I think that's really fundamental. At the same time, we don't want to isolate teams, because then we run into a lot of strange social traps like fundamental attribution errors, and we may get long lead times between the teams. So we need to make a distinction between what I call the operational boundaries and the knowledge boundaries. So there are several ways of achieving that. So your operational boundaries, the parts of the code where you spend most of your time, should be relatively small, right? So your team should carry a meaning from an architectural perspective. I think that's important. But your knowledge boundaries have to be much, much broader. So there are several ways of achieving that. One is to start to invite people from other teams to your code reviews and design walks to get to know them and exchange context, get to know each other. Another thing you can do is to encourage people to rotate teams. Not everyone wants to rotate a team, but if they want to do it, they should be free to do it. And the third thing is to, what I've seen work really well is this open source ownership model, where a team kind of owns a piece of code in the sense they take the responsibility. Anyone can make changes to it, but the team has the final say on what's going into the code and whatnot. That is actually worked quite well because it takes away this bottleneck, right? If I need to make a change to this part of the code, I can do it. I don't have to wait for someone else. So whatever you do, make it a conscious and deliberate decision, because this is not something that will happen automatically. Hope I managed to answer the question.
So there were a lot of questions about the tools you were using. You did show that on the slides. Still, which one did you actually use to do the visualizations that you have in your presentation?
Oh yeah, so I used CodeSyn for that because that's kind of my life these days. The actual visualizations, you can use whatever tool you want to do them. You can. I started out just using Excel. You can actually get pretty far with that. D3 is wonderful at visualizing data like that. That's what CodeSyn uses for most of the visualizations.
Isn't focusing on hotspots making them even hotter?
It depends on what you do with them, of course. So yeah, I mean, in the short term, of course, when you start to refactor a hotspot, it may indeed lead to increased activity in that hotspot. However, what you shall see, what I typically find is that most really, really scary hotspots, what happens with them when you refactor them, and refactoring a hotspot is not something you do like, all right, let's refactor it, let's start this week and let's finish in 2 months. So it's something that has to be an iterative process, right? Where you make smaller and smaller improvements over time. So they should actually cool down over time, and many hotspots just go away because they don't exist in the new design. They are represented by different design elements. And during your refactorings, you should see a noticeable drop in complexity if you start to measure trends like that. So you can actually, and that's another one that ties back to a question I got about how to sell this stuff to management, right? Is that you can show them that, hey, look, we're actually getting a measurable effect of our refactorings.
How can you create code ownership?
How you create code ownership?
Yes.
I don't think you can. I don't think you can create. I mean, again, whatever model you choose. I mean, I've seen everything, and I've seen a lot of different styles that work. I think the key is really to make it a deliberate choice. Decide upon one model and go with it.
Okay. Okay, final question. Have you used SonarQube?
No, I haven't used SonarQube. I do use a lot of static analysis tools. I used to, back in my days when I was a .NET consultant, yeah, it's true. I used NDepend a lot. I use, now I do Closure these days. I use other static analysis tools for that. And I'm actually a big fan of static analysis, right? I just think the issue is that we need something on top of static analysis. We need techniques like this to prioritize and say, hey, this is where we should start to address those findings that the static analysis tools gives us. So it's just another input source. And I think they complement each other quite nice.
Okay, thanks a lot again. Thanks a lot for the great talk, and hope to see you sometime.
Yes, thanks. And please come and grab a bunch
Yeah,
of CODES
there are
Primes and
stickers.
stickers.